Hello, students. This is Dr. DA again, and for my wonderful students at Long Beach City College in my Chem 1A class, this is a brief practice session. We're going to practice working with chemical reactions in aqueous solution and doing some stoichiometry calculations in the process. So let's go ahead and move over to our whiteboard. Let's review a few things of what we're going to learn in this practice. Number one, we want to practice writing out chemical equations or reactions that happen in aqueous solution. In this particular case, we're going to focus on a precipitation reaction. The other thing we're going to practice here is once we have a balanced equation, how do we use it to calculate the theoretical yield? And if we know what the amount of product obtained is, what is the percent yield of the reaction? Okay, so let's go to our practice problem. This is our practice problem. I'd like for you to maybe pause the video, and if you want to take a screenshot so you can work on it separately on a piece of paper or on a separate electronic device, perhaps. So it says here that 100.0 milliliters of a 1.200 molar silver nitrate solution are combined with 100.0 milliliters of 1.200 molar solution of sodium phosphate. A precipitation reaction is observed. The precipitate is collected by filtration and weighed. Okay, first of all, make sure you understand what the experiment is. We're mixing two aqueous solutions. A precipitation occurs, which is a solid product, and we filter the reaction mixture. And on through a pre-weighted filter paper, we weight the resulting combination of filter paper and residue. And of course, we can calculate how much residue was obtained. So there's 4 questions here. What is the identity of the precipitate? What is the balanced chemical equation? What is the theoretical yield? And if the actual amount of precipitate obtained was 10.85 grams, what was the percent yield? Okay, again, let's take a moment to think about our strategy. First of all, although you were not required to be told, you should have probably predicted this, we can see that a precipitation reaction is observed. Number 1, what is the identity of the precipitate? So let's read a few of these things. First of all, the first thing we want to do is make sure that we have the compounds that are involved in here. So we have silver nitrate and we have sodium phosphate. So let's see what those are. Silver nitrate. First of all, as soon as we see compounds that have silver and sodium, we know that these are what kind of compounds? Correct. These are ionic compounds. So what we want to do is we want to go to the periodic table or to our table of ions and find out what these are. It will be good, and you will be given this in an exam to look at this table here. This is our periodic table. But you remember we got this table earlier in the course. It's a table that has all of the different ions that we've been working with. And at the top are the polyatomic ones, and the bottom are the monatomic ones. And we know that we have silver nitrate and sodium phosphate. So, of course, that silver and that sodium are going to be in the form of ions, right? So we need to find what these ions are. So I think that we can go in here and we can find silver, and we have it in here. That's a silver ion. And over here we have sodium. And those are the two that are going to be involved. Then the other 2 ions that we have are phosphate and nitrate, right? So we have the silver is combined with nitrate. So we're going to have to find it here in the top part of this table. And here is our nitrate ion. And it has a -1 charge. Where is the phosphate? Oh, here it is. Here's the phosphate. And as you can see, it has a -3 charge. Okay, so if you want to pause the video now, you might want to now go ahead and write these out and see if we can come up with the formulas for these compounds, okay? In the meantime, I'm going to scroll up here, back to our problem. Here we are. So we're going to be going out to question number 1. We're going to try to find out what is the identity of this precipitate. Oops, sorry, I made a mistake here. Okay, here we go. So here we go. Silver and nitrate. So silver, we said is Ag plus, and we said nitrate is -1. So if I combine these two in order to form a compound, the compound would be Ag and O3. I need 1 silver for every nitrate ion. Now the story with sodium and phosphate is a little bit different because sodium is +1, but we said the phosphate ion has a -3 charge. So remember, one thing that we taught you is one way of doing this is perhaps to basically do a crossover where one ion's charge becomes the other ion's subscript, right? And so this guy would be then Na3PO4. So we have now the formulas for our two compounds. Now remember, when a ionic compound is dissolved in water, what you get is that the ions will dissociate. Say ions dissociate in water. In other words, the form that we're going to get in water is going to be more along those lines. So this guy here, and I'm trying to draw a square here, but I don't know if you can see it. Okay, those are the species that are going to be present in water. And so in water, these guys can combine. And so the idea is that if any combination of one of the cations with any of the other anions gives you a compound that is no longer soluble, you're going to get a precipitate. Now let's see who it is. So in this case, what we could do is we could postulate, well, let's see, who could we have? So we could have silver combined with phosphate, or we could have sodium combined with nitrate. Now, when you combine those, remember that, again, we're going to have to do a crossover here. So this will be Ag3PO4, and this would be simply NaNO3. How do I know if either one of those compounds is going to give me a precipitate? Well, for that, I need to go to my solubility chart. And you should have this bookmarked in your notes for the purpose of all these practices. In the case of the exam, I will give you that chart. Now let's go scroll down here and find it. See if we can find it down here. Oh, here it is. This is one of the different kinds of solubility charts that you might find. So the idea is that there are two sections here. The top section tells you compounds that are generally soluble when they have the particular ion listed in there. In the bottom, you have compounds that are generally insoluble when they have that compound there. So one of the things we find is up here that if you look at the nitrate ion, you can see that it is generally soluble with no exceptions. So any compound with nitrate is going to stay in solution. Now let's think about the other guy, the phosphate. Well, we can see down here that phosphate is in the category of compounds that are generally insoluble. Now, there might be some exceptions. So let's see what the exceptions are. Well, if it pairs with lithium, sodium, potassium, or ammonium, the resulting compounds are soluble. That's why the initial solution of sodium phosphate was perfectly soluble. But now what we're trying to form is one that has silver. Since silver is not listed here as an exception, and compounds that have phosphate in them are generally insoluble, we can go back to our two candidates here, up here at the top. Let's see if we can find it. Oops, let's see, here it is. And we can see now that we have this is that our sodium nitrate will remain in solution, but our silver phosphate will be solid. So the answer to question number 1 is the precipitate is Ag3PO4. In other words, silver phosphate. Okay, let's now tackle question number 2. And remember that one of the key things in writing a balanced chemical equation is to remember that make sure you have the correct formulas. And also you indicate the correct physical states. In this particular problem, that is very important because remember that the key of this reaction is that one of the products is no longer in solution. So we had already in the first part identified the formulas of these guys. So what we're going to have here is we're going to have, okay, so we have silver nitrate plus sodium phosphate and our products are sodium nitrate, which we said stays in solution, and silver phosphate, which we said is going to precipitate. And don't forget that this silver has a 3 there. Now remember that when you balance an equation, once you have the formulas written down, you cannot change the formulas themselves. All you can change are the coefficients. So I'm going to leave some blank spaces here in front of these guys just to make sure that we have the proper space here for them. And I mean, the way you do this depends. So what I have recommended is that you basically run a bar here, and then you list out all the species on each side. So on the left side, we have silver, we have sodium. Now we have these polyatomic ions, nitrate and phosphate. But we have said that in these types of reactions, where there's simply an exchange of ions, the polyatomic ions play as if they were a single entity. In other words, we don't try to balance the nitrogens and the oxygens and the phosphorus atoms. We're basically going to treat the nitrate as if it were an entity and the phosphate as if it were a single entity. Now we see how many there are on each side. And we see at this point we have 1 silver, 1 nitrate, 3 sodiums, and 1 phosphate ion. This is going to simplify the balancing if we keep the polyatomic ions as single entities. Okay, let's look at the right side. We're going to have the same elements because matter has to be conserved. So the same species are going to be in here. And let's see what the numbers are. In this case, we saw that we have 3 silver atoms. We have 1 nitrate polyatomic ion. We have 1 sodium, and then we have 1 phosphate. And again, I say atoms, but of course we understand by that I mean, the ion of that particular guy. Now, when balancing the equation, what we want to do is try to start with a compound that is present on only one, start with an element that is present in only one compound. Now, in this case, because of the, dual exchange or the double replacement or double displacement, however we call this, it's relatively straightforward to do this. So let's say, for example, that I say that I want to start out by balancing the silver atoms. Well, it's obviously clear here that we have on the right side of the equation, we have 3 silver ions, whereas on the left side, we only have 1. So what we're going to do is, how about if we start with that? So the way I do it is I am going to introduce a multiple of 3, okay, over here in the front. And what that's going to do is going to change the number of silver ions into 3. I'm going to indicate this over here by a forward slash, and I'm going to put a 3 in there. And this is going to be step number 1 in our process. So I'm going to put this a parenthesis 1 here, parenthesis 1 here. Now, as a consequence of that change, because the coefficient affects the whole set of units in the compound, that means that I now had to consider that I've not only multiplied silver by 3, but also the nitrate ion by 3. I'm going to indicate that by using a reverse slash or a downward slash like that, and say that I now have 3 here as a result of the change in item number 1. This is change number 1. Now, what I see here is that now that I have 3 units of nitrate on the left, now on the right side, I can see that I am short because I only have 1 unit of nitrate on this side. So what I'm going to do is I'm going to go up here where it says sodium nitrate. And how about if I put a 3 in there? This will be step number 2. And as a result of step number 2, I'm going to end up having 3 units of nitrate in here. But remember, when you multiply nitrate times 3, you're also multiplying the sodium. So in other words, now the sodium got affected also by this change. And so I'm going to indicate that with a backward slash and say that I now have 3 here as a consequence of step number 2. So again, if you want to pause this for a moment and recap, kind of like recap, notice that what I'm doing here is for every coefficient that I change, I'm calling that step a number in parentheses. And I'm indicating in the table below what are the quantities that are affected by that change. So change number 1, which involved putting a coefficient of 3 in front of the AgNO3, not only gave me a change from 1 to 3 silvers, it also changed NO3 from 1 to 3. Now, since on the right side, I only had 1 nitrate, I put step number 2 in parentheses, which involved putting a coefficient of 3 on the top. And that also affected the number of sodiums. So I indicate down here where the sodium ions went from 1 to 3. And again, notice that any change that I directly caused by forcing that coefficient, I'm indicating with an upward or kind of like forward slash. And then any change that occurred as a result of that intervention, I'm indicating with a downward or reverse slash. And then I put the number in there. As we can see, we now have a balanced equation. Up here. And over here, we have our balanced equation. And we're going to use that one for the next step in the procedure. Okay, we have our balanced equation in there. Again, I apologize for my poor handwriting, but I never said I'm a good calligrapher. Okay, let's tackle now question number 3. So question number 3 has to do with what is the theoretical yield of the equation? In other words, how many grams of precipitate? So here is what I usually recommend that we do with this kind of question. Essentially, they're going to ask us to navigate a stoichiometry sequence here. And the way it works is typically, here's what I tell you to do. Number one is to ask yourself, what are they asking for? In other words, what do they, the powers that be, what do they want? And the answer is we want grams of precipitate, in other words, grams of product. Then I ask the question, well, what do they give me? Again, I'm going to use this. What do they give me? The answer is they're not giving us grams or stuff. They're giving us milliliters of solutions. So the question now is, how do I get from what they give me to what they want? Just remember, in this roadmap that we're going to build, the chemical equation is transacted in moles. So what you have is going to be moles of reactant and moles of product. This is the way the reaction is transacted always. This is the currency of the chemical equation, moles of reactants and moles of products. The question is going to be, how do I get from milliliters of solutions into moles of reactants, and how do I get from moles of products into grams of products? Well, since in this case the product is a solid, the conversion between moles and product is what? Please pause and think about this question and see what answer you come up with, and then come back to the video and let's see what it is. Okay, hopefully your answer was, I need the molar mass. That's going to be my conversion factor. So that I can get from the moles of products into the grams of product. Now, how do I connect moles of reactants with moles of products? Again, pause the video for a moment and see if you can answer that question. Okay, the answer would be you're going to use the coefficients in the balanced equation. The next question is, how do I get from milliliters of solutions into moles of reactants? Please pause the video and think about it for a moment. Okay, hopefully the answer you came up with was the molarity of those solutions. Okay, if you were not sure about any of these, please pause the video and go back and review some of our discussions in class, in lecture, about how to work with chemical equations when the substances are present as solutions of a known molarity. Okay, so let's go back now and answer the question. Okay, now that we have the balanced equation and we have a roadmap for how we're going to do this, we realize that if we're going to convert between moles and stuff like that, we're going to need some data here. So first of all, what we're going to need is we're going to have to figure out, well, if the product is going to be measured in grams, we need to find out, well, what is the molar mass of silver phosphate? And for that, of course, you're going to have to go to the periodic table. And I have one in here. And of course, in the scenario of an exam, you will be given this very same periodic table, and you'll be able to use it. And this is all belonging to previous units, so you should all be able to do this, how to calculate the molar mass of a compound. In this case, we're trying to find out what is the molar mass of silver phosphate, and you should all be able to find out that it is a total of 418.58 grams per mole. Please pause the video and do this calculation, and please confirm that that's the value you're going to get. Okay, now that we have that, please let's go ahead and figure out how we're going to do this. All right, so let me navigate here a little bit. Again, I hope that you were able to confirm that that is the molar mass that we're going to use for silver phosphate using the periodic table that you would be given in an exam situation. Now, how do we go from, first of all, from the amounts given of reactants into the moles of product and into, therefore, the possible yields? So when we talk about theoretical yield, one thing that we had to take into account is that each one of these reactants would be capable of giving a particular yield. So when we are talking about the theoretical yield, one thing you're going to have to figure out is who is the limiting reactant, right? And we do that by calculating, well, what would be the yield from each reactant present in the amount that they are present? So what we're going to do then is we're going to take that, and let's start out with our silver nitrate. So we have silver nitrate, and it says there that we have, in our problem, it said that we had 100.0 milliliters of 1.20 molar silver nitrate. So we're going to say here we have 0.1000 liters of silver nitrate solution. And we can use either the parenthesis or the grid method. I'm going to use parenthesis in this case. Now, our next step, remember in our strategy, we're going to find out, well, how many moles is that? Well, it says here that we have 1.200 molar, so that's 1.20 moles of silver nitrate in every liter of solution. And what that'll allow us to do is to cancel out the liters, right? Now remember, we had to now make the transition from moles of reactant to moles of product. So according to the chemical equation that we balanced, we said that we get 1 mole of silver phosphate for every, don't forget, 3 moles of silver nitrate. And again, this is going to allow us to cancel out the moles of silver nitrate. And remember, the last step in our approach was to say, well, how many grams of product does that represent? So let's go ahead and do that and say we already calculated, according to our thing up here, that 1 mole of silver phosphate is 418.58 grams of silver phosphate. There you go. And so now we have, in the last step, we have a cancellation of the moles. And so we are left with units of grams of silver phosphate. Before you put any numbers into your calculator, make sure that this roadmap that you tracked in here gives you the correct units at the end. So let me give you a few moments. Please pause the video and work on the calculation and see what value you get. Be mindful of sig figs. Okay, now that you're back, we'll see what this is. And oops, let me get that out of there. Get us back into the black color. And here we go. So I have 16.7432 grams of silver phosphate. Okay, I wrote it in 4 decimal places because typically that is what our analytical balance is capable of measuring, right? However, notice that in the numbers that we were given before, these values here only had 4 sig figs to them. So technically, if you're going to go, kind of like very strict about sig figs, only these first 4 digits would be significant. So it'd be 16.74 grams. And if that were the answer, that would be it. But we're not done yet. We now have to figure out, well, what is the yield based on just the other reactant, which is sodium phosphate. So let's go ahead and do that. Let me let you pause the video here. What I want you to do is now repeat this process using now the sodium phosphate reactant and see what the yield would be for that particular reactant. Please pause the video and work on those calculations and then come back. Okay, here are the numbers that I have. Please confirm your calculations. Please look at the path in the line there where it shows the different steps, the different conversions, and then what you got at the end. Now, again, this would technically only have 4 sig figs, but you can already see that if sodium phosphate were the only substance reacting here to the completely, it should yield 50.23 grams, whereas silver nitrate only produce 16.74. So essentially what we say is that the reactant that produces the smaller yield, that is the reactant that is limiting. And therefore, that is the maximum yield that you can get. All of that reactant will be consumed in the reaction. It'll give that yield. The other reactant will react partially, and there will be some leftover afterwards. And so, therefore, the answer is that our theoretical yield is 16.74 grams. Like I said, in a real experiment, since you are actually weighting this product, your analytical balance should be able to register 4 decimal places of mass. And therefore, certainly you would be closer to the 16.7432 amount that we calculated here, but which we rounded down for the sake of significant figures. Remember that ultimately significant figures are determined by the quality, by the certainty of the instruments that you use and the measurements that you make, not simply by whatever rules or calculations you're making. Okay, so let's go ahead and go to the last question in this series. Okay, we have one more question. Sorry that I forgot to put a number on it, but it's this one over here. If the actual amount of precipitate obtained was 10.85 grams, what was the percent yield? So remember that ultimately, if you are doing this kind of work, there's always a goal in mind. You have to produce something, and you want to say, is the process that I used the most efficient? Am I getting a good yield for what I do? So remember that percent yield. Oops, sorry, let me get my pen back here again. when we say percent yield, this is something you need to remember. You're going to be talking about what is the actual yield divided by the theoretical yield times 100%. So in our case, we said that according to this problem here, the actual yield was 10.85 grams. Our theoretical yield, we said, was 16.74 grams times 100%. I'm going to let you pause the video here and see what value we get. Okay, the number you should get is 64.81%. We're going to limit this again to 4 sig figs in the given number. Remember that our theoretical value was deliberately truncated to 2 decimal places just because we wanted to follow the rules. But technically, you could have weighted the product to 4 decimal places. However, the number they give us here is limited to 4 sig figs, and so we are going to limit our result to 4 sig figs. So please check your numbers and make sure that this works for you. Okay, students, I hope that was helpful. In this practice, we looked at how to build the formulas of ionic compounds, how to predict what will happen if there is a precipitation reaction and predict what is the precipitate, and then utilize the information given to build a balanced chemical equation and use the information in that equation and the information given from the experiment to calculate the theoretical yield and the percent yield of a reaction. If you have any questions, please don't hesitate to send me a message or come by my office time and we can discuss it some more. Thank you so much.